Tonight's video guide here is to help us review for the test we're going to have on Friday over reaction types and factors that affect reaction rates. To begin with, there are 4 types of reactions that I expect you to know for the test. You should know synthesis reaction, decomposition reaction, single replacement reaction, and double replacement reaction. A synthesis reaction is a reaction between 2 reactants forming one product. And so our general formula is A plus B forms AB. Now, I could go ahead and give us an example of magnesium plus chlorine forms magnesium chloride. Now, chlorine here is 2 atoms put together. It's one of the diatomic elements I said you could have on the periodic table, and that includes hydrogen, oxygen, nitrogen, fluorine, chlorine, bromine, and iodine. And so if I do this, after I write out my reaction, the first thing I'm going to do is I'm going to make myself a T-chart here. And I'm going to say I have 1 magnesium on the reactant side, 1 magnesium on the product side. I have 2 atoms of chlorine on the reactant side and 2 atoms of chlorine on the product side. The next step that I'm going to look at here is on my product side, do I have anything besides the product I'm trying to make? And so I'm trying to make magnesium chloride, and so I only have MgCl2 present on the product side. And then I need to determine, are both sides balanced? Same number of magnesiums and chlorines on each side, and this is also true. The last part is how many atoms of each of these did I need? I only needed 1 magnesium, so I'm not going to change anything here. I only needed 1 pair of chlorine, so I'm not going to change anything there. And then I only created 1 magnesium chloride, so I'm not going to change anything there. But if I needed to, I would put the number out front, and I'll show you an example like that here in a second. For a decomposition reaction, this is similar to a synthesis reaction, except for now we only have 1 reactant, and this is going to break apart into multiple products. And so the general formula is AB breaks down to form A plus B. If we did an example of this, I could use H2O2, which is hydrogen peroxide, and it's going to break down into H2O and oxygen. When you're deciding what you need to add to both sides, if there is not a plus sign separating the elements listed, in the case of H2O2, then you need to add the whole thing, even if you only need 1 more oxygen. So to begin with here, I'm going to put my 2 hydrogens and my 2 oxygens, because that's what's indicated by H2O2, and I'm going to put that also on the product side. Now, on the product side here, I could have H2O and then O2. Right now I have a single molecule of water, but I only have 1 oxygen when I need 2 of them. So I'm going to have to go back to the other side here and add additional hydrogen peroxide. In doing so, I'm going to make another water molecule, and I'm going to complete our pair of oxygens there. In this example here, it took 2 hydrogen peroxides to form 2 molecules of water and then a single pair of oxygens. Single replacement reactions are similar in balancing to synthesis and decomposition, but now we have an element and a compound are going to react to form a new compound and a different element. And so the general formula is A plus BC forms AC plus B. One additional step that you need to do with this is you need to check the reactivity of metals from page 333. If the element that you're reacting with the compound is higher on that table, it's more reactive, it's going to replace the metal involved in the compound. If it's below, no reaction is going to take place. And so let's look at an example here on the next slide. If I were to take lithium and add it to calcium bromide, okay? Ideally, what's going to happen is we're going to get lithium bromide plus calcium. When I look at that table on page 333 in the textbook, which you can have on your periodic table, we find that lithium is higher on the table than calcium, so this reaction will take place. So to finish up this problem here, I need to do just like before and balance it out. Now, the plus here indicates that I can either add lithium or additional calcium bromides as needed. I do not need to add both every time I need an additional atom. So I'm going to start by writing that I have one lithium on each side. I'm going to go then ahead and take care of my calcium bromide. And I'm going to organize the bromines based on what I'm trying to make. Now each lithium bromide requires only one atom of bromine. And so I've got a complete lithium bromide right here. But then I have this additional bromine by itself. And so I'm going to have to go back and I'm going to have to add an additional lithium to both sides. And so it takes two lithiums plus a compound of calcium bromide to form two lithium bromides and one calcium. Double replacement reactions are very similar to the previous examples, but now it's two compounds reacting to form two new compounds. So my general formula is AB plus CD is going to form AD plus CB. And so the products for a double replacement will always include at least one of the following. There will be a precipitate present, there may be gas formation, or a covalent compound will be formed. If we look at our examples here of a double replacement, and I do FeCl3 plus NaOH forms FeOH3 plus NaCl. I'm going to start by putting my reactants on my product side. And I'm going to organize my chlorines based on what I'm trying to form. I'm going to do the same with the sodium hydroxide. Now looking at this problem, I still need an additional 2 hydroxide ions and I need an additional 2 sodium ions to go with my missing with the chlorine atoms there by themselves. So I put 2 more sodium hydroxides on the reactant side, and they go on the product side also. Now when I calculate this, it takes 1 iron chloride plus 3 sodium hydroxides to form 1 iron hydroxide plus 3 sodium chlorides. The last part that's covered by this test here is reaction rate factors. And so we've already done a lab on this where we looked at concentration, temperature, catalyst, and surface area. So from our previous examples here, the more concentrated a sample is, the faster it's going to react. And the reason this is that there's more molecules present in the mixture, and collisions have to happen between the reactants for a chemical reaction to take place. Temperature is responsible for the kinetic energy of those molecules. So the higher the temperature, the faster they move. The lower the temperature, the slower they move. A catalyst, as previously explained, is a chemical compound that you can add to a reaction, and what it's going to do is it's going to speed up the reaction, but it's not going to be consumed in the reaction itself. So this is for reactions that would take place on their own, like the decomposition of hydrogen peroxide. But we could add manganese dioxide to take it from taking a month to decompose down to a couple minutes. The last reaction rate factor is that of surface area. As explained in the classroom here, the more surface area you have, the faster the reaction, because the chemicals need to be in contact with each other. And so the unexposed portions aren't going to react until the outer surface is reacted.